In 1933, at the Century of Progress World's Fair in Chicago, General Motors wanted to show off this new technology, but people didn't understand the concept of invisible magnetic fields. So they placed a newspaper in between a stove and a metallic pot. They boiled the water in the pot, but the newspaper didn't burn. It blew people's minds because for 5,000 years, cooking meant fire or a hot surface. They called it cold cooking, what we know today as the induction stove. Induction stove works on the principle of electromagnetic induction. Electromagnetism, electricity and magnetism are effectively the same thing. It's like this illusion. It looks like a duck, but if you tilt your head a bit, you could see a rabbit. Is it actually a duck or a rabbit? It's both. It depends on your perspective. Flowing electrons in a wire, or simply electric current, creates a magnetic field around it. Now, if you could change the magnetic field in a coil, that creates an electric current. That word is so important. Changing magnetic field. How do we change the magnetic field? Let's say we have a bar magnet. It has a magnetic field around it. The magnetic field lines run from the North Pole to the South Pole. I'm going to place this magnet closer to a coil. Some of these field lines are passing through this coil. We call it magnetic flux. I'm moving the magnet in and out so that the number of field lines passing through the coil is changing. Magnetic flux is changing. And whenever there's a change in magnetic flux, a voltage will be induced in the coil, which in turn creates an electric current. Okay, now back to the case of induction stove. Stove plugs into AC power. We use alternating current or changing current to create changing magnetic field. Typically, we get alternating current of frequency 50 Hz or 60 Hz from the power socket. That is, the current oscillates 50 times or 60 times in 1 second. But that's not enough. So using an inverter, this is converted to a very high frequency of 20,000 to 50,000 Hz AC. A metallic pan is placed on the top of the induction stove. So basically, the pan is now in the changing magnetic field. That creates a current in the pan. If you have a wire, there is a specific path through which the electrons can flow through. But for a metallic surface, the current will be all over the surface. These swirling loops of electricity are called eddy currents. Simply consider it as the current flowing through the metallic surface instead of a wire. The metal offers resistance to the flow of this current as the electrons collide with its atoms. This creates heat. In iron pans, the magnetic field flips the magnetic atoms back and forth, creating even more heat. We make use of this combined heat to cook food. But there's a problem. We can't use just any metal. For example, copper and aluminum. They have very large skin depth compared to that of iron. What is skin depth? When direct current flows through a wire, it distributes across the entire cross-section of the wire. However, when alternating current flows through a wire, it tends to crowd towards the outer surface or the skin of the conductor. This is the equation to find the skin depth, the effective depth from the surface of the conductor where most of the electrons flow. Delta is the skin depth, rho is the resistivity of the conductor, omega is the angular frequency, and mu is the magnetic permeability. Decreasing skin depth increases the resistance and thereby heat, as more electrons would get squeezed into a smaller area of cross-section. Skin depth is inversely proportional to the magnetic permeability. So to minimize skin depth, we should use a material of very high magnetic permeability. That is a ferromagnetic material like iron. That being said, there are other variables you can play around with that change the skin depth, like the angular frequency. If you increase the angular frequency to around 100 kHz or higher, even pans made of metals with low magnetic permeability create enough resistance to produce heat. This is how all metal induction stove works. But it comes at the cost of lower efficiency, around 70 to 75% for copper compared to about 90% for iron. But most induction-ready pans are just cheating. They have the steel disc glued to the bottom, stove heats the steel, and steel transfers the heat to the aluminum on the top. So in short, the heat is not produced in the induction stove, but in the pan itself. That magic trick from 1933 was a clever application of Faraday's law. By turning the pot itself into a heat source, we have finally moved past the need of fire